Previously we looked at the Dijkstra algorithm and it didn't feel terribly efficient. Now, why was that? Well, let's oversimplify the case and look at this very, very basic network. And again, we want to go from alpha to omega, which is over there. And we're starting here and we look at the costs. It costs us 3 to go there and 1 to go there. So obviously we go with the cheapest path because that's how our algorithms work. 3 is greater than 1, okay, and so we're there. We look at this, and 3 is greater than 2, yep, so we've ended up there. 3, well, now they're equal. It's cost us 3 to get there, and it's going to cost us 3 to go there. So, if we want to be favourable towards this, we want to be going that way. So let's just say, let's have a look at that. And we get there, and that's cost us 6, and 6 is greater than 3, so we're back there again. So we go there, 6 is greater than 4, which is the cost of getting through here so far, and 6 is greater than 5. We've got all the way out to H over here, and got to the end. And it's the wrong way. I mean, we wanted to go over there. So why did we go over there? Because the cost through the network was always less, or almost always less, that way. So our algorithm, our naive Dijkstra algorithm, pushes us this way in the wrong direction, despite the fact that we want to go that way. So we'd have to do all of this unnecessary analysis before we can even start really looking at the way we know we need to go. We need to go over there, so we want to go left. We need some way of telling the computer, go left, not right, because that's where we want to go the other way. So how do we do this? Well, we add a little more information to the Dijkstra algorithm, and then we call it the A-star algorithm. We add in some other piece of information. That piece of information, in our case, for our spatial network, is going to be the straight line distance, as the crow flies from our destination. So here's our destination again. It's still omega down there. It's the same network as before. The distance to omega from omega is 0. With that's the destination. There is no distance from it. The distance from alpha up here is 14, I'm saying. The distances I'm going to show now are actually approximately correct. I measured them with a ruler on the screen. Not a very good way of doing it, but it'll work for this demonstration. So 14 units from omega up to alpha there, and then from A it's 13. It's slightly shorter. I think you can see that. It's a slightly shorter distance to get to omega from there. So that's the distance as the crow flies, ignoring the network, just the straight line distance from node to node, from there to there. And we continue that over the entire network, and we can see that the closer the node is to our final destination, the lower this red value, the Euclidean distance from one node to the final destination node. So that's extra information that we can add in. So how do we do this? We go back to our stack of cards and we add an extra column onto the stack of cards. We still have this, the weight, the cost of traveling through the network by these values on the lines, but we add to that in this fourth column here now, we take that and add to it the distance, the straight line distance from our destination. So when we look at our first 3 cards again, we're standing on alpha. The weight is 0, but the distance is 14, so that sums to 14. A has a cost of travelling through the network of 4 initially, that we know, and a distance of 13. So that adds up to 17, whereas B has a distance through the network of 1 and distance of a straight line distance to our destination of 10. And that sums to 11. And for C, we have the cost of travelling through the network of 3 plus 12 is 15. It's quite simple. And then we move on to our analysis. We reorder them by this right-hand column. And the next one in line is B, which has a value of 11. Good. We pull up card number F because we can see that from B. And that has a cost of 4, but a distance of 6. So that just adds up to 10. And we can see that 10, even though the 4, the cost of travelling through the network is higher than for these others, for A and C, we can see that this right-hand column is actually the lowest value. So by reordering according to this right-hand column, F comes to the top directly. So now we can move down there, and then when we analyze f, we can see that omega then turns up there. The cost of traveling through the network is 7, and the distance added to that is 0 because that's the final. So that just becomes 7 down there. And that gets us to the end very quickly. We didn't have any of that messing around, traveling around over here. There is no guarantee that this will give you the fastest route. It's more likely to. We've added this extra information, but it is entirely possible, of course, that in a much more complicated and larger network, there could be a high expense incurred to begin with that then can be compensated for by a very cheap network farther down, but we don't access that network properly because of this idea of just examining this cost, the distance. We've traveled down here very quickly, ignoring whatever might be happening over here. That could, in theory, occur, not always though. This is likely to be a very good solution.